Good day, viewers. Once again, I welcome you to this moment in mathematics. So, we are going to continue with solution to polynomial equation part 2. So, in particular, we are going to look at the factorization method. Okay? And we'll leave the graphical method for now. So, continuing with the factorization method, okay, so now the topic in particular we are looking at is quadratic equation using the factorization method. Now, remember I said in my last lecture, or in my last class, that the factorization method involves using Viete's equation. Okay, so now, how do we make use of this Viete's equation? Before then, we look at the general expression of quadratic equation, which is given as ax squared plus bx plus c equals to 0. So this can be, we can take this our general expression of quadratic equation. So if we suppose that this equation is factorizable, suppose this equation is factorizable, if we want to solve it by factorization, then it means that there are two factors that when we multiply, it will give us this quadratic expression. In other words, for this quadratic equation to be factorizable, that means that I can write this as ax squared plus bx plus c is equals to x plus alpha into x plus beta. Okay? Where alpha and beta are the roots, call this equation 1, are the roots of equation 1. Okay? Now, basically what we want to do now is, because I told you that before now that if we want to solve quadratic equation by factorization, what it simply means that given any quadratic equation, it can be placed in this manner. Okay? But then, we've already assumed that it can be placed in this manner. Now we want to see, beyond placing it this way, what process is involved, or what process are we necessarily going to have on ground so that we can have this expression to be in these factors, multiplication of these two factors. Okay, all right. So now, if I call this one equation 2, if I expand this, x plus alpha, x plus beta, if I expand it, I will have it as x squared plus if x multiply x, I have x squared, and if x multiply beta, I have beta x. Next, I have alpha times x, will give me plus alpha x. Next, I have alpha times beta, will give me plus alpha beta. If I take like terms, I have x squared plus alpha plus beta x plus alpha beta. Okay? Now, if I call this equation 3, call this one equation 3. If we compare this equation 3 and equation 1, if you look at equation 1, you observe that the coefficient of x in equation 3 is, the coefficient of x squared in equation 3 is 1, and the coefficient of x squared in equation 1 is a. So I want to transform this equation 1 so that the coefficient of x squared here will also be 1. Okay? Because we say that a polynomial, two given polynomials are equal if their corresponding terms are actually equal. So what I will do now, I will write this equation, I will divide 2 by a. If I divide this equation 1 by a, I have x squared plus bax plus c over a equals to 0. Okay? So call this one equation 4. So comparing this and this equation and this, you can see that the coefficient of x squared here is 1, the coefficient of x squared here is 1. They agree. The coefficient of x here is alpha plus beta, while the coefficient of x here in this equation 4 is b over a. So by implication, it implies that alpha plus beta is equal to b over a. Then here you have the constant term here, independent of x, is alpha beta, while the constant term here, independent of x, is c over a. So I have my alpha beta is equal to c over what? A. Now, this is actually what we call the Viete's equation for quadratic equation. Okay. Now, but oftentimes you observe that if we want to make use of this, if we want to move from this place up here, you know, that what I mean, if we want to look for two numbers so that we add it up, it gives us b over c, and we multiply it b over a, and when we multiply it, it gives us c over a. Sometimes it's not, it doesn't come that easy because of this fraction part we have here. Okay, so it will be a lot easier if we can, you know, simplify this expression or this equation so that we do away with the fraction. Okay, so in order to do that, I'll multiply across with a. If I multiply across with a, then this equation will reduce to a alpha plus a beta equals to b, and this one will be a alpha beta equals to c. Okay, a alpha equals to c. Now, let me, as you can see now, we don't have any fractional or rational expression there. Okay, so let me call this one equation 5. Now, we say let p be equals to alpha or a alpha. Let p be equals to a alpha, and q equals to a beta. Okay, if that is the case, this equation 5 will become p plus q equals to b. But for me to bring in p and q into the second equation of the system in equation 5, I'll do a little bit adjustment. I can multiply further across with a. If I multiply this one with a, I have a squared. If I multiply this one with a as well, I have a here. So that if I cancel off with a, you know, I will get the original equation. So by multiplying both sides of the equation with a, we've not done any harm to the equation. So if that is the case, then that means that I can write this here as a alpha into a beta. So that if you multiply across, you have, or if you multiply through, you have a square alpha beta. Okay? So that Now I can now put my P here and my Q here. So that I'll have PQ is equals to AC. Okay. So call this one equation 6. Okay. Now this is what we call, you can call it the modified Viete's equation. And call this modified Viete's equation. Okay. Oftentimes this is actually what we use while trying to factorize a quadratic equation. One can either say find two numbers so that when you add it, it gives you the coefficient of x, and when you multiply it, it will give you the multiplication of a and c. Okay. So now, and when you get this number, when you get these two numbers, what we normally do, you plug it in here, and then factorize. Okay. So then let's see now how it will go. I want to use this modified Viete's equation to factorize this particular polynomial. Okay. Now, remember we moved from here and we got this. Okay. Now, suppose I don't know this, I want to move from here to this again. Remember I told you that sometimes working with this fractional part, it may not be, you may find it a little bit difficult to get. So it's easier to work with this. Okay. So the question now is, given this quadratic equation, suppose we have this, or suppose we know this, can we factorize this? So we now see how we can do that. Okay. So I have this quadratic equation, a x squared plus b x plus c. It will now be, I have my b to be equals to p plus q. Okay, so I'll have a x squared plus into p plus q. Okay, x. Now I have my c from the second equation. If I make c the subject of the formula, I'll have pq over a. So I'll have plus pq over what? A. Okay. Now this all equals to 0. This is all equal to 0. Okay. Now if I multiply both sides by a, if I multiply across by a, I will have a square x square plus a p plus q x plus pq equals to 0. Okay. Now if I allow this a to go in, if I open up this, I'll have ax r square plus apx plus aq x plus pq equals to 0. Okay. Now, of course, ax is here, a is here. Also, in this, if we consider these two terms, a is here, as is here, as is here. So if you consider this one, q is here, q is also here. So we can collect them in pairs. So that I have ax square plus axp plus axq plus pq all equals to 0. I collect items. Ax is here, I have ax into ax plus p plus q is here, I collect q into ax plus p equals to 0. Okay. Now ASP is common. If I factorize ASP, I'll have AX plus Q into AX plus P equals to 0. Okay? So by this it means that equals to 0. We've gotten that two factor. So this implies that ax squared plus bx plus c is equals to ax plus q, ax plus p. So we've actually factorized this equation. Then note further, if actually this multiplied by this equals to 0, it means that each of them, so the implication of this is that one, we have this quadratic equation has been factorized in this manner. 2, it means that ax plus q is equals to 0, or ax plus p is equals to 0. So if I make my x subject the formula, I'll have my x is equals to minus q over a, or x is equals to minus p over what? A. So now the implication of this in factorization is that once you can get the number p and q, you may not necessarily need to substitute this p and q into this quadratic equation and start the process of factorization until you get to this point. No, once you get p and q, it is already established that x is equal to minus q over a, okay, and the x is equal to minus p over a. Of course, you can get that from here. Remember, we say alpha is the root, alpha and beta are the roots of that quadratic equation. So that from here, if I say from here, you can see that by implication from here, alpha is equal to p over a, and the beta is equal to q over a. Beta is equal to q over a. Okay? So now, but from this particular, you have q over a, and this one you have p over a. But then you observe that the difference between x and x we have here, alpha and beta we have here, are just the negative sign, which I can replace this as minus p over a, p over minus alpha, and this I can replace as minus beta. And recall from that expression we have x plus alpha into x plus beta. And when you equals to, if you solve this, you have x equals to minus alpha and x equals to minus what? Beta. So which agrees with what we have. Alright? So in general, I will state this as a theory, so that with this theory you can actually apply it whenever you come across any quadratic equation. Maybe I will do that in my next lecture. Thank you. I remain your humble presenter. Please don't forget to like and share this lecture. Thank you. Goodbye.